In this video, I want to introduce the idea of a breadth-first search in a graph. A breadth-first search, or a BFS, is a particular way that we can traverse a graph, meaning basically walk through all of the nodes in our graph. So let's say we have the graph here, and let's say 0 is the node that we want to start from. I've denoted that with this little s here. There are many different patterns or ways that we can traverse this tree. We can go from 0 to 1. So like, let's say we start by processing 0, then we go to 1, and then 3, and then 5, and we're continuing down this path. Instead of doing this, a BFS is going to go level by level. It's a traversal that goes level by level. So you would start with the 0 node. So we process that. Then you go to the 1 node and then the 2 node. And this is one level. And then the 3 node and then the 4 node, and that's another level. And then the 5 node, that's another level. So if you notice, we can almost draw rings around the 0 node, or partial rings, right? There are like these levels that we are processing one level at a time. We first did this level with the 1 and 2 node. Then we did this level with the 3 and 4 node, and then we did this level with the 5 node. That is the essence of a BFS. We call that a level order traversal. And BFS problems are oftentimes pretty easy to identify based on the patterns or some clues that you can identify in the problem. And a BFS is a level order traversal. That just means it goes level by level, like we discussed. So if you ever see a problem that wants you to do a level order traversal, there's a very good chance a BFS is how you'll want to do that. Another thing is that a BFS is a really good way to find the shortest path between two nodes. You can imagine that if we did a level order traversal and we wanted to find the shortest path between 0 and 4, then we would know as soon as we hit 4, we've found the shortest path, because it would be like this. Whereas you can imagine if we go sort of in an alternative way, like I mentioned earlier, we could go like this, and then this, and then this, and then this, and we've already passed the 4 node, but we don't even know. Right, so the length of this path is already, well, it's covering 1, 2, 3, 4 nodes and 3 edges. So you can say the length is 3 or 4, whatever you want. But we've already passed the 4 node. But by doing a BFS, you know that you're finding the shortest path because you're going a level at a time. So these nodes are only 2 edges away from our start node of 0. You go to 1 and then you go to 3 or 4. So if you ever see something about a level order traversal or a shortest path question, there's a very good chance that you want to use a BFS. Okay, so with that being said, I want to talk about how we actually implement a BFS. And the most important thing is that we want to go level by level. We want to go in order of start with the first level that's closest to us, then the next level, and then the next level. You can imagine when we're at this 1 node, we want, so we started the 0 node, right? We process that. Then we get to the 1 node, and we want to store, hey, 3 and 4 need to be processed, but before we actually process 3 and 4, we have to process 2. So we finish 1, and we take note of these guys. Let's say we put ends to say, hey, take note that we need to come back to them, but next go to the 2 node. So we're going to need some sort of data structure that is going to hold these nodes and tell us 3 needs to be processed, just not yet. And we are going to do that using a queue because of the fact that the first thing put into the queue is the first thing that comes out of the queue. And I think that's easiest to see by an example. So let's say that we have a queue that I will define up here. So let's say it's just going to be, we'll kind of diagram it out as just a large array. And we're going to start with the 0 node. So the very first thing we'll do is we'll put the 0 node onto the queue. I'm going to be writing numbers in the queue, but I want to be clear that we really are putting the entire node inside of the queue. So we put the 0 node in the queue, and what we're going to do, and that's just kind of how we initialize this to set it up. Now our process is going to be remove 1 node from the queue. So let's just say we go to the 0, we grab it and move it out, and then we process that node Now, for our example, it's pretty straightforward. All we want to do is just take note of who its children are so that we can process them later. So we know that the 1 node is a child of 0. So we add it to the queue to say, hey, process this later. And then we also know that the 2 node is a child of 0. So we're telling our queue that this needs to be processed later. Now that's it. That's all we want to do with our 0 down here. I'll go ahead and erase that to show that we are done messing with it. Next, we're going to pop another node off the queue. So we're going to prop this 1 or remove this 1 from the queue. And we're going to do the same thing. We're going to say, hey, add my children to the queue. And you can see this is the value of the queue with the BFS. Because when we add 3 and 4 to the queue, you can see that they are still after 2. And this is key. This is how we go level by level. Because all of the nodes that are in this level right here, I can actually outline it, in this level here, will be processed before the 3 and 4 nodes, since they are added to the end of the queue, and the nodes from this level right here would already be in the queue. Okay, so next we can erase our 1, and now we're going to want to move 2 out of the queue. So we move it out, we process it, and we say add any children that we have into the queue. Well, we don't have any children, so it doesn't really matter. So we can erase the 2, and now we move on to the next node. So we say we're going to process this 3 node, so we move it out of the queue. We say add any of my children to the queue. So 5 is the only child. And now we can delete the 3 node. Now we move the 4 node out of the queue. We say process any children I have. We have this 5 node here. Let's just assume this node has already been added to the queue. So we don't have to worry about it. So we can go ahead and erase this 4. And lastly, we're going to pull this 5 out of the queue. We're going to realize it has no children. There's nothing to add to the queue, so we can just erase it. And now our queue is empty. These commas are not important. And now that our queue is empty, we realize, hey, we finished our BFS traversal. So we were able to go 0, 1, 2, 3, 4, 5. So we went in the proper order. And this is the conceptual idea of how a BFS works. Now I want to talk about the time and space complexity of a BFS. So first, let's define our variables. So we're going to say that V is equal to the number of vertices in our graph. So we can say vertices. And remember, vertices is just another word for nodes. So that V is also the number of nodes in our graph. And E is going to be the number of edges in our graph. This is pretty standard across graph problems. Now, the time complexity, well, let's go ahead and think about this. We know that adding something to a queue takes constant time. And every single node should be added to the queue at least once, right? So that alone means that if we're looking at time, this is not our final answer, but sort of brainstorming here, we understand that it's at the very least it's going to be O of V, right? Because every single node or vertex is added to the queue one time. But if you think a little bit further, what do we do for a particular node? Let's say the 1 node. Well, we are iterating through every single edge that it has. So you can think we're sort of doing, you may think we're doing O of E work, but not precisely, right? Because we're only on the 1 node iterating through this edge and this edge. So it's only 2 nodes. But if for every node we iterate through all the edges it has, in total, we are doing O of E work. I'll say that again. If for every node we iterate through the edges that it has, in total, we are iterating through every edge in the graph and doing a total of O of E work. So this is going to be, we'll say, we're doing O of V work, but we're also doing O of E work. So our overall time complexity is actually going to be O of V plus E, because we touch every vertex and we also have to, throughout our entire algorithm, iterate through every node. Iterate through every edge. Okay, now in terms of space complexity, the space is going to be determined by our queue. So really this question comes down to, what is the maximum size of our queue? And to answer that question, we can draw out the sort of worst case scenario. So let's say we had a node like this. This was our starting node, and then it connects out to a bunch of different nodes. So let's say we have some here, 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 and here. Well, the way this is going to work is we will initially add the central node to the queue, and then we're going to pop it off, remove it from the queue, and process that node. And when we do, we add all of the other nodes into the queue. So every single node from our graph, except the starting node, is going to be added to the queue. So you can imagine that in that scenario, the space complexity is going to be O of v minus 1, right? Because we are processing every vertex except for one of them. And we know with complexity, we don't care about a minus 1 if we have v. So the overall space complexity is going to be O of v. Because in the worst case scenario, you could have all of your nodes except for one inside of the queue. So that covers the overall complexity breakdown of a BFS, along with what it is and how it uses a queue. I want to discuss a quick note about how we implement a BFS in JavaScript. A lot of people, when they need to create their queue, they'll do something like this in JavaScript. They decide they can just use the built-in array. Whenever they want to add an element, they'll just use the push method. And whenever they want to remove an element, they'll use the shift method, because that grabs you the value at the beginning of your array. This is actually not the best way to do it, because you can imagine, let's say we had a case like this. Here, if we do array.shift, we delete this one element, but we actually end up having to shift every single element over to the left by 1 so that we have a proper array that starts, with index 0. So what this means is that this actually runs in O of n time, where n is the length of the array, because of the fact that we have to move every element over. So instead, in your interviews, you probably don't want to use the shift method and a normal array to have your queues. Instead, you probably want to use a specific queue data structure. Usually your interviewers won't require you to build one out from scratch, as long as you kind of define how you're interacting with that queue data structure. So something simple like, it'll be a class that will have an enqueue, dequeue, size, and isEmpty method. And for the purposes of the problems on InterviewAce, I'm just going to use this queue here that I've written in advance. I'm just going to import it at the top of my files so that we will be able to actually test the code with a real queue. In terms of your practice, LeetCode will actually already have a queue class, so you can just pretend like there was one imported at the top of your files. And I've made sure that the methods I have on my queue class are identical to what you see on LeetCode. So you can basically just, when you're working on LeetCode, pretend like you have the same import and queue class that you're working with, and copy what I'm doing, at least from the queue interaction side of things. That's it for this note. I just want to be clear that you shouldn't use an array in JavaScript when you're doing a BFS. Instead, you want to use a specific queue class so that you can implement your dequeue method in constant time instead of linear time. All right, that's it, and thank you.